And like I said, when we started this section, we're only going to look at this one example. So if you have any issues with graphing in this section, please ask in class and we can talk about it as well. Also, reminder that a lot of these homework questions in 4.4 do already provide you multiple choice graphs. So just, don't be tempted to just look at the graph and then try to base your work off of that. If you can, in preparation for the exam, graph those by hand and then compare your sketch of the graph to the possible choices is the best way to handle that. All right, let me go back here. We were graphing the rational function f of x, and we determined the domain, vertical asymptotes, x and y intercepts. And so all of that pretty much above that line there, that's kind of stuff we should know, right? If we don't remember how to find vertical asymptotes and horizontal asymptotes from an algebraic perspective, then I certainly hope you remember the calculus approach where we look at limits to do that. Does anyone have any questions on any of that information? And then we looked at sort of the new stuff we've developed here in chapter 4, that is intervals of increasing and decreasing, local extrema, using the first derivative, and intervals of concavity and inflection points using the second derivative. All right, and so I've copied our sign charts for the first and second derivative, because in addition to the kind of basic information, what we're going to do is put all of this together to give us a shape, if you will, of the original function. And the first and second derivative, meaning the first and second derivative stuff, is going to be put together to give us one of these four shapes that, depending on the function, we stitch together to get a whole picture of the function. All right, so let's summarize then our results from the first derivative. Since the first derivative is always negative, what does that mean about f of x? Oh, I didn't quite copy this correctly. Remember, these were our vertical asymptotes here. So the first derivative being positive or negative tells us what?
Increase or decrease.
Intervals of increasing and decreasing. Okay. So let me make sure we didn't summarize that already. I think we might have just mentioned it. Oh, okay, we did. F of x is decreasing. If you misread this chart and forget that the function's undefined at -1 and +1, then you might be inclined to say that the function is increasing from -infinity to +infinity, and that's incorrect. To say that the function is decreasing on its domain is a correct thing to say, because we've already identified the domain. So if we say the function is decreasing on its domain, by implication we're saying that it's decreasing on the intervals that aren't including 1 and -1, which we've explicitly listed here. Okay. Did we summarize this? No, I don't think we had enough time to summarize our second derivative stuff. So let's go ahead and do that here. Let me start a new page. I think that page is pretty long, and if you're referring back to the notes, the print might be really tiny. So let me start our second derivative stuff back here on this page. Okay, and so what does that tell us about f of x? Looking at the second derivative, f of x is, identify a few things here. Second derivative tells us about what? Yeah, concave up, concave down, concavity, and in the analogy of the local minimum and local maximum test on the first derivative is where concavity changes, which tells us our inflection point or points. So f of x is, let's just say, concave down from -infinity to -1, not including, and from 0 to 1. So just a reminder, the function was undefined at -1 and +1, so we have our vertical asymptotes there. The second derivative yielded a single value where it was 0 or undefined, and that's this value of 0 right here. Okay. And then the original function f of x is concave up on the interval -1 to 0, and from 1 to infinity. Make sense? Any questions? Okay, we do have change in sign of the second derivative, so we do have inflection point, or points. I'll just write that out. Okay, so where would our inflection point be? At x equals to 0. A change in concavity. So when and sometimes it's subtle, but when your function goes from concave up to concave down, we would have an inflection point right here. So the analogy to that is when the first derivative changes sign, we have a local minimum or a local maximum.
I feel like I vaguely remember on the homework them just asking for the x-coordinate of the inflection. Is that right? Or like on the exams, will you be asking for like an actual point? Or if you just say identify inflection points, can we just put x equals 0?
Yeah. Yeah, you just have to be mindful of the instructions. So if it says identify the x-coordinate at which this function has a local minimum, maximum inflection point, then that's sufficient.
Okay.
But really when we describe a local minimum, local maximum, or an inflection point, they are actual points on the graph.
Okay.
So, I've seen there is tendency to get a little mixed up because, especially when you're describing both inflection or concavity and intervals of increase, decrease, because you're using the first derivative, the second derivative, and you're plugging stuff back into the original function, right? So it's really hard initially to keep things straight. When we find our critical points of the first and second derivative, the test points that we've chosen here in red are always plugged back into the derivative. It's only when we want to know something about the function where we plug those values back into the original function. So really the only time you're going to utilize the original function is if it says what's the point of the local minimum, local maximum in an inflection. That's when you would take that x-coordinate of the critical points and plug those back into the function. So that's really the only time that you reference back the function, unless you're looking for other additional points to plot, which you shouldn't need because we're already doing enough with the graph itself to generate a pretty complete picture of the function. So is everyone clear on that? You should only reference the function when you're finding the y-coordinate of inflection points and local extremes. So I hope that helps. In practice, it can get confusing, which is why you have to practice this. All right, well, we have an inflection point in -1 or +1. We change concavity there. So we change concavity here, inflection point here. Would we have an inflection point in -1 or +1? No, why not? Because what? Yeah, our function's undefined there, so we've got a vertical asymptote, or asymptotes, rather. All right. Any other questions on the second derivative stuff?
Is that second concave up? Is that 1 to 0?
Yeah, negative, so concave up from -1 to 0 in this interval, and then from 1 to infinity. So yeah, I said infinity, but I wrote 0, yeah. So concave up from 1 to infinity, thank you. So then it's almost like now at this point to get the individual pieces, we're gonna visualize like superimposing the test for the first and second derivative together to give us a picture of the original function f of x. And so we had our, let me do this. We had our vertical asymptote here at -1 and at +1. That was involved in both the first and the second derivative. And then the second derivative came in and had a 0 when x is equal to 0. I should have scooted that over. I'm gonna enlarge this a little bit so things aren't so cramped. So then we're putting, like I said, the pieces of information from the first and the second derivative onto the representation for f of x. So we had f of x was decreasing from -infinity to -1. So f of x is decreasing there from -1 to +1 was also decreasing. Just exaggerate this too. And decreasing here as well. Okay, so that was the information from the first derivative. And then the second derivative, we have the fact that f of x is concave up from -1 to 0 and from 1 to infinity. Concave down from -infinity to -1 and from 0 to 1. So you do make, when you're drawing f of x here, not only including the asymptote, hopefully that's obvious, but the critical points from the first derivative and where the second derivative was 0 or undefined. Is everyone clear on what we're saying here? Let me just draw out another scenario. Let's say -3 and 5 were critical points on the first derivative, and the second derivative maybe has 2 more critical points here at -1 and +1. Okay. When we are looking for the picture for f of x, we would want to make sure that we're putting all of those onto f of x, because the second and first derivative described different things for us. So we would have, here at -3, -1, +1, and +5. And so in each one of these intervals here, it's going to be either increasing or decreasing, and concave up or concave down. So we want to make sure that we identify both of those in each one of those kind of partitions. Does that make sense, or was that just confusing?
Makes sense.
All right, and so once we have these descriptors, then we're referencing back these 4 things here to give us a sense of what the graph looks like in each partition. right, so if f of x is decreasing and concave down, would f of x be above or below the x-axis and for a decreasing and concave down? Keeping in mind that we do have this vertical asymptote here. So we're on the left of the vertical asymptote. We've determined that the function is decreasing and concave down. Would that be up here or down here? It's below the x-axis. There's our horizontal asymptote. So remember the shape of decreasing and concave down. Remember, decreasing means if I go from left to right, that the function falls. So decreasing, we fall from left to right, and it's concave down, so we've got this particular kind of shape. There's no way that can be above the asymptote, because then it would look like this, right? So that's not a viable solution. That piece has to be here, decreasing and concave down.
Hey, Cody. This is the worst classroom that you've been in. So I actually had another observation.
Oh, all right. Yeah, no worries. Okay. All right. Is that clear? Does everyone understand why that piece is down there? Yeah.
And the reason it doesn't go above the x-axis is because there's no critical point, right?
Right. Well, it doesn't go above the x-axis. Because we can look at it in that way. There's no other critical point, so we know that it's not going to change back from positive to negative again, or increase or decrease. It's always decreasing here. And the other reason is because we have this horizontal asymptote sort of guiding that. Is that helpful?
Yeah.
Okay. All right, next interval, let's get this up a little bit. From -1 to 0, the function was decreasing and concave up. So again, we're gonna pick back up here. If it's decreasing and concave up, it's gonna look like this. Well, let's draw it up here. Decreasing, falling from left to right, and now it's concave up, so it's gonna have that sort of curvature. Would that piece go above or below the x-axis? Above. Again, that's the only option for this thing to do, is to be like this. What happens as we get closer and closer to the origin? Is what?
It's going to get closer to 0.
Yeah, it's going to get closer to 0 because we know we have an x-intercept and a y-intercept at that point. So we're going to get close to the origin and touch at the point 0, 0. So there's our x and y intercept. All right, there's our piece that's decreasing and concave up. Are there any questions on that? Okay. From 0 to +1, decreasing, falling from left to right, and concave down. This should have left a little bit more room. So our piece from 0 to +1 takes that shape. And we know there's nothing goofy going on at the origin, right? There's still a point there, so we have to go from this point, decrease down here, and it has to be concave down. And we're going to follow the asymptote there. And since we're just looking at this information, you know, there's really no way to tell how drastically the graph curves. We're just labeling our information and sketching the best possible graph from that information. All All right. Finally, from 1 to infinity, the function is decreasing, falling from left to right, and concave up. So we have that piece. And where would that go, above or below?
Are you deciding that it falls from left to right because it's decreasing?
Right.
Okay.
Yeah. If one of these were increasing, then from left to right, we would draw something like this. So if it's increasing and concave up, we would do that. If it's increasing and concave down, we would have that. So yeah, just make sure you're familiar with these 4 outcomes on that first page. Are there any other questions?
What if you didn't have the horizontal asymptote? Like, how would you go about it? Because wouldn't that be the reason that it can't be above if it's like decreasing, concave down?
Yeah, so if we didn't have the horizontal asymptote, then, you know, it might be something similar to like a trig function or a polynomial, to where you would end up with, you know, intervals of increasing and decreasing, kind of generating, you know, curves like this. You know, I don't know, that's pretty bad, but you end up piecing it together that way or piecing them together this way. So in that instance where we wouldn't have a horizontal asymptote, the first derivative would come in and say, hey, you've got a local maximum here, a local maximum here, and a local minimum here and here. So you would also be able to use that information to kind of decide where you're turning around. Does that make sense? Not all of the graphs we'll see will have asymptotes. All right, the last piece, where does that have to go? Above or below the x-axis? Above. So it's decreasing, concave up.
Why do you decide it's above and not below?
Well, so if it's decreasing and concave up here, then we would have to, it would have to be like this to fit in between these asymptotes, right? So that is increasing,
But it's not increasing.
and it's concave down, but it's increasing if it's below. So we wouldn't have that piece. We would have
Oh, I see what you're saying.
that piece. Okay. Any other questions? So there's our graph. Let's actually graph the function and see how close we got. So not bad, right? It's pretty close. Ours maybe a little bit too curvy at the origin, around the origin rather, but nonetheless, it's a fairly accurate representation. And you know, it's a lot more efficient than just choosing, you know, 5 or 10 points and seeing what's happening, right? Okay, so there we have it. Any questions on that problem? So that will conclude 4.4. And we'll start 4.6. So in 4.6, we're looking at, excuse me, linear approximations and differentials. And don't let the word linear approximation scare you. We've actually already done this. It's just, it's taking on a different flavor in this section. So maybe you recognize the process, we'll mention it, but the idea is that if I look at a function, say this curved function here, as I get closer and closer to any particular point on the curve, the function looks more and more like a line. It looks more and more straight. So this red line here at P on that function is what? Think about chapter 3 and what we spend a lot of time in chapter 3 doing.
Tangent line?
Yeah, it's the tangent line. So the tangent line from chapter 3 is just rebranded here as the linear approximation. So when you see the linear approximation, it's no more than finding the equation of the tangent line. Okay. I just want to zoom in on this part of our curve here, just to further illustrate that. If I'm close enough to a curve, there's no way to distinguish whether that's an actual curve or it's a line. And so that's really the point in this section. Since we've looked at the equation of the tangent line just as a thing, we said, hey, this is the equation of the tangent line. Cool, I found it, right? Well, what good did that really do us? We were just mathematically finding a line that was tangent to a point. So here we're going to show one application of what that can actually do for us. So I mentioned here in chapter 3 it says find the equation of the tangent line at a point A, f of A. In chapter 4, this is going to be rebranded as the linear approximation. So although we have a new labeling, we have already done this. For those of you that are going on to Calc 2, this plays a pretty important role in approximating functions, because what you'll see in Calc 2 is that the linear approximation is valid, but if we look at a quadratic approximation, then it's a little bit better. If we look at a cubic approximation, where it's x squared, x cubed, then it's a little bit better. X to the fourth approximation, even better, etc., etc. So you'll see that many functions can be represented as an infinite polynomial. In fact, when you type in on your calculator, like e to the 0.2 power, your calculator is using that fact to calculate e to the 0.2 power, or the natural log of 1.75. It's expressing the natural log or e or whatever function as a polynomial, and your calculator is using the polynomial to compute that value instead of the logarithm or the exponential or the trig function. So this is sort of like the tip of the iceberg in that procedure. And honestly, with computers and calculators, it's really hard to sort of justify this section. As with a lot of sections, it's like, well, why can't we just type in the square root of 1.1 into our calculators and get the exact value? Why on earth would I go through the process of finding a tangent line and then plugging all of that into a line instead of just punching it in on my calculator? And the answer is you wouldn't. In practice, at the job, you're using a computer or a calculator to calculate these things. You don't really need to approximate things, right? But if you're out in the field and you don't have your phone or your computer, then you could get a quick idea of what's happening using a simple approximation. So just kind of keep that in mind as we move forward. Don't look at it through the lens of, why are we doing this because I have my calculator that tells me what it is. Look at it through the lens of this is a part of something much larger. And if you're not going on to Calc 2, unfortunately, you don't get to see that, but it is worthwhile to investigate. I hope I sold that pretty well. I'm not a salesman, but. Okay, so here's the definition of the linear approximation to a function at an x value, x equals to a. That is, at the point a comma f of a. Okay, so the function's differentiable. What did differentiable mean? When you think of differentiable, what do you think of?
Derivative exists at that point.
Yeah, the derivative. So differentiable means that the derivative exists. So the function has a derivative that exists on an interval containing the point, or containing the x value, x equals to a. And the linear approximation is defined as follows. So instead of saying that this is the equation of our tangent line, we're going to label that as capital L of x, just to kind of distinguish between the two. So capital L of x is our linear approximation, defined as f of a plus f prime of a times x minus a. So just want to also point out that in chapter 3, when we did find the equation of the tangent line, at a comma f of a, we said was y equals to, well, let's look at it this way. We said y minus y1 equals to the slope of our tangent line times x minus x1, right? That's kind of where we started with that point slope formula. So notice here the only difference is that with this particular notation, the y1 is this f of a. So we have y minus f of a equals to the slope of our tangent line times x minus x1, which is a, x minus a. And then solving for y, we would add f of a to both sides. So that was the equation of the tangent line and how we described that in chapter 3. So just compare that to the linear approximation. You see it's the exact same thing. The only notation here, difference, is that we're denoting the slope of the tangent as m tangent, whereas here this is f prime of a, which is, we know that's how we get the slope of the tangent line. We find the derivative and then plug the a into the derivative. And just as in chapter 3, I want to point out that this right here is a number. Not a function. Initially, when we find the derivative, it is a function of x, but once we plug in a, it's no longer a function of x, it outputs a single number. So I just want to mention that because I do see that a lot with linear approximations. People want to just stick the derivative as a function of x right there, which is incorrect. So it seems like a lot of information. Do y'all have any questions? Okay, so find the linear approximation is equivalent to find the equation of the tangent line. And so we'll look at this example in two parts. Find the linear approximation to sine x at x equals to 0. And then we'll use the linear approximation, I abbreviated that LA, linear approximation, to approximate the sine of 0.01. So part A, I'm going to find the linear approximation, or the equation of the tangent line at 0 at the point 0 sine 0. That is at the point 0, 0. So remember, just as you go through this section and find linear approximations, to label it as such. Capital L of X. Okay. So the first step in doing this is we need to find what?
Derivative.
The derivative. So let's find f prime. So f prime of x is what? Derivative of sine is cosine. The next step is to do what?
Plug in A.
Plug in A. So now we're going to evaluate. Now we're going to evaluate the derivative at the given A value, which was 0. So the cosine of 0 is 1. And then this is the number we're using. That's the slope of our tangent line at the point 0, 0. Okay. Now we just put all of that information, the point and the slope, into point slope formula, and we have our linear approximation. Well, I should say point slope with and tangent being 1, and the point is at 0, 0. Okay. So we could go through that process like we did on the previous page. If you just want to remember that the linear approximation, we just take the y-coordinate, f of a plus the slope of the tangent x minus a, that's fine too. It's really just saving you the step of having to add or subtract the y-coordinate to the other side of the equation. So we have capital L of x, our linear approximation is the y-coordinate of the point, 0, plus the slope of our tangent line, times x minus the x-coordinate. So it simplifies quite nicely because that's just L of x equals to x. So that's the simplest linear function that we can possibly have. Do you have any questions on the process? Okay, so what does that tell us then? We know it's the equation of the tangent line on sine at the origin, but really what does that actually do for us here? So let's go back here. So what we found to the original function f of x sine x, we found the linear approximation. But what does that actually mean? We have a way to approximate the sine function linearly. So how does that help in any way?
Doesn't it just give us the slope at whatever point we want to find it at? Is that what that is?
So the derivative function cosine x would give us the slope at any point we want to find that at. We've sort of set that in stone once we said evaluate the derivative at 0. So that's now like very concrete. We're specifically on the sine function at that location, 0, 0.
It's telling us that it's increasing.
Do what?
That it's telling us that it's increasing. Like, that matter?
Yeah, so this linear function here is increasing. So we could say that at the origin the sine function is increasing. But the idea is that the linear approximation is approximately the original function. So instead of evaluating sine of x we can use our linear approximation, which was just x, to approximate sine x as long as we are near the origin and the fact of the matter is that as long as we're near the origin is because we constructed our tangent line at x equals 0, which gave us the point 0, 0 on the sine function. In other words, if we looked at the sine function and got really, really close to the origin, the point where we constructed our tangent line, then the sine function would look exactly like the line y equals to x. Does that make sense? That's the entire point of linear approximations. So think about that first page when we zoomed in on a curve and we said if we're close enough it looks like a line. That line is represented by the linear approximation. So here it's the line y equals to x. So let's look at that. So there's our sine function, and there's L of x. So notice, if we're not close to the origin, like out here, then it's still pretty easy to tell this is sine, and this is our linear approximation. But if we get close enough to the point at the origin, we virtually can't tell the difference between the sine function and the simple function y equals to x, which was our linear approximation. Let's label these things here. So the second part says approximate sine at 0.01. So instead of actually computing the value of the sine of 0.01, we're just going to use the linear approximation to tell us that value. 0.01 is really close to the origin, so we would expect that if we're right here as an x value, then using the line to tell us what the value of the sine function is shouldn't be too far of a stretch, right? It should be super, super close to one another. I think it was 0.01. Yeah. So are there any questions at this point? Yeah, 0.01. So now we're ready for part B. We found our linear approximation. And so we're going to use the linear approximation to approximate the sine of 0.01. So like we notated earlier, the sine of 0.01 is approximately our linear approximation at 0.01. So I don't know what the sine of 0.01 is, but I know what my linear approximation is. It's just x, meaning whatever I plug into my linear approximation, I'd get out as the output. This is super easy to evaluate. What we put in, we get out. So what we're saying is, based off the linear approximation, the sine of 0.01 is 0.01. Does that make sense? Do you all have any questions on that? Yeah.
So you said as long as you're near, how, what would near
Right.
be?
Yeah. So we said as long as we're near the origin, then this is a good approximation. The question was, how near do we have to be? It's really an ambiguous term. It varies from function to function. Although we don't get into that type of analysis, we could talk about it because we already have the tools to talk about it. It's based off of the second and third derivatives and higher order derivatives. So really here we could look at the second derivative and talk about its concavity and then use that to discuss what does near actually mean for this particular function or any given function. But to us, that near is it's very arbitrary, nebulous. For comparison, this is really all we're doing here. Your homework does actually have you compute the actual value, just to kind of see where your approximation is with respect to the function's actual value. So let's compute the actual value to see how far off we are. The actual value of sine of 0.01 is what?
0.009999.
0.00?
And then 4 nines.
9. Okay, was that approximation close? Yeah, it's super close. Let's see if we can modify this. Maybe go to 0.5. Oops. I just want to look around that region that we're discussing here. Okay. Oops, need to go here. So we'll find 0.1. So we're approximating the sine of let's turn the line off here, approximating the sine of 0.01. sorry, 001. Where's that at? All right, so we're using the line, not sine function, to approximate that. So kind of keep that value in your mind here. And so notice I'm turning on the line, and we're this close. You can't even see the line, because it's directly on top of the sine function. So let's see how close we actually have to get if this software will actually show us the difference between that. It might not. So there's, everybody see the 0.01 down there? Okay. So there's the difference between the sine function at 0.01 and our linear function at 0.01. It doesn't even, the difference doesn't even register on the computer. Look, it's, the output is 0.01, the output is 0.01. We clearly see there's a tiny difference there. And we just essentially have measured that tiny difference. The difference between our approximation 0.01 and the actual value 0.009999. So try to capture this scale. Okay. Does that make sense? Hopefully, like visually seeing that helps us kind of reconcile what we're actually doing with the math. Do y'all have any questions? Okay. I think it's only a couple more minutes to break. So I do want to look at one more thing, and when we get back from break, I'll have y'all work on an example. But what I want to show you at this point, since we don't have time to start a new example, kind of what we were alluding to earlier with using the linear approximation and then the quadratic and then the cubic, etc. I'm going to move it back to the origin. Okay, so here's what we found. We found the linear approximation to the sine function at the origin. And just for reference, we'll keep that point the same and look at the quadratic approximation. Sorry, not the quadratic approximation. Why wouldn't sine have a quadratic approximation? Or why wouldn't it make sense? What kind of symmetry does the sine function have?
Continuous, going from -1 to 1.
Okay, certainly true. If I reflect the graph over the origin or over the y-axis, would that be symmetric? Imagine the origin is the spine of a book, right? If I open or close the book, it's not the same thing, is it? If we're symmetric with respect to the y-axis, what kind of function do you have? An even function. So sine is not an even function, sine is a odd function, right? So approximating sine with like x squared, x to the fourth, x to the sixth doesn't make sense because those are all even, right? Sine is not an even function. So here what we're looking at, as we can see from the purple graph, that's a cubic. But notice we'll get a little bit closer to the origin. Notice how much better, as far as how far I can move away from the origin, that cubic approximation is as opposed to our linear approximation. So, out here is where the linear approximation and the sine function start to deviate. We look at the cubic approximation over here at this kind of peak in this trough. We get a little bit more coverage on the sine function. Okay, so I'm going to just move this, and we're going to get the third degree, the fifth degree, the seventh degree polynomial that approximates sine. And just notice on the ends how much more of the sine function gets filled in. It's funny, it looks like it's waving. or something dancing. So see, okay, here's I'm not sure how this is programmed, but this is like a 19th degree polynomial approximating sine, as opposed to a linear approximation, a degree 1 polynomial, right? So you could imagine carrying on that process out to infinity. What we would get is complete coverage of the sine function. Whereas the ease here is this is a line, now it's a third degree polynomial to a 19th degree polynomial. It might be debatable as to whether or not plugging an x value into a 19th degree polynomial is easier than plugging it into the sine function. But at least we know how to square and cube numbers, right? So anyways, that's kind of the bigger picture of what this builds into. There's a lot of physics applications, optics. There's certain optics equation that use sine, and for like really small measurements, typically they just use the this linear approximation, y equals to x, in lieu of the sine function for that optics equation. As long as those those measurements are really, really small, then this is sufficient instead of using the sine function. Okay. Do you have any questions? All right. So we'll take a break and then work a few more examples. So there's one more thing I want to mention, particularly when working with trig functions. If you remember that all of our derivative formulas were, specifically with trig functions, were with respect to x being in radians. So that's why, hopefully at the beginning of the semester, you turned your calculators into radian modes, or mode. So you can be asked to approximate like the sine of 30 degrees using the linear approximation. You just want to be mindful that you convert the degree measure into radian measure before you plug that into your linear approximation. So recall the derivatives of our trig functions. Were defined with, the independent variable x being a radian measure So if you were asked to compute, talking and writing. compute or approximate let's say the sine of I don't know, like 0.3 degrees, you have to convert that degree into a radian measure. So you convert into radians before you plug into the linear approximation. Okay, so just remember that. And once this linear approximation has been established, then you basically can approximate all of the values of sine near the point that you constructed the linear approximation or the tangent line at. So, going back up to our linear approximation, if it said approximate the sine of, I don't know, 3 pi over 1,000, then the sine of 3 pi over 1,000 is approximately 3 pi over 1,000. We're using that linear approximation, which is y equals to x. So, a couple of other examples. Like the sine of pi over 72 is approximately equal to the linear approximation evaluated at pi over 72. And again, our specific linear approximation was just x itself. So the linear approximation evaluates to the input. So the sine of pi over 72 is pretty much pi over 72. The sine of 3 pi over 1,000 is approximately the linear approximation at 3 pi over 1,000. And that linear approximation at that value is that value. And so on and so forth. We could continue with that. But so as you would expect, not all linear approximations are y equals to x. It really depends on the function and the point you're constructing that about or around. Do y'all have any questions? All right, so I want you to try this example. To find the linear approximation to y equals to the square root of x at a equals 1. So that's like part A, and then part B and part C, if you will, are going to be to use the linear approximation to approximate the square root of 1.1 and the square root of 0.1. So I'll go ahead and write the actual values for these. That's fine. We'll talk about more. So what did you do? Okay, yeah. So you want to be careful here because that's where your input goes.
Yeah.
This approximation is that L of x is approximating the square root of x. Right? So this evaluate L of square root of x. Now you're doing square root of square root. So you're right. This approximation.
Just give us problem, we do it. What if we don't have anything at all? Is there just a separate?
So far, so good.
On this is the information on this desk, it will just come with the
Yeah.
It's kind of like your.
Okay, yeah.
Oh, yeah, that's like this. Latest tea. Richard.
Yeah.
I don't guess anything he said. They get a lot from the book.
I didn't write that as far as.
Okay, so this is going to be this one.
It's home, and I kind of got used to it. I just
On this one half.
We're getting used to this.
From your work. That's 1 plus 1/2 x minus 1/2. So you that's just like this harder, this constant.
Wrong algebra. No, don't look, it's not ready.
The one.
So you gotta take that assumption of the square root of 1. You've already approximated the square root by this. So you should plug in. Put that here. It's a little bit. It's 8. So that's the square root of 1. It's
If we do just like.
okay. There is a yeah. Yeah.
Okay. So now we just plug in the dot and these.
Yeah, so that's your,
But
yeah,
it's in
you
here.
use that line to approximate.
Got it.
Sort of,
Yeah.
yeah. That really helps us figure out. Right before the exam. That helped. So here, this is linear approximation. This one, this is the function, approximates this function. This line approximates the square root of some number. So you plug in the sum for the square root of the number here. You just want to plug in the number here. To approximate the square root of 1. Yeah, so to approximate that. Because you have the square root. Okay, so you have the linear approximation. That's what this line here approximates this function. This line approximates the square root of into a line. Then you would say, so when you evaluate
Does he?
That's roughly half.
All right, it seems most of you got the linear approximation, which is good. That's definitely the bulk of the work here. But there was some confusion on what we're plugging in. So let me just get this down. So we all ended up with, 1/2 x plus 1/2, or x plus 1/2, same thing, or 1/2 times x minus 1. So remember, the whole idea of any linear approximation at a particular point is that whatever function we're given is approximated by the line. Also note that the input for the linear approximation just as a general thing, the thing that we input into our linear approximation, that number only goes right here because A is fixed. This is going to be f of A is a number, f prime of A is a number, and A is a number, right? So whatever you plug in, it only goes right there. All right, so that's what we're using. We're using our linear function. And saying that that linear function is approximately the function we started with, right? The linear function, 1/2 x minus 1, is approximately the square root of x, and we'll just make this small note for x near 1. So the square root of 1.1, this is where some of the confusion was surrounding. The square root of 1.1, our x, or the thing we're plugging in, is just 1.1. So we want to evaluate our line at 1.1, not the square root of 1.1, because the line approximates the square root of some number. So that square root of that number is already accounted for in that tangent line. Okay, so our linear approximation at 1.1 is this right here.
It should be
and
plus 1, by the way.
do what?
It should be plus
Oh, it should be plus 1. Why did I write minus 1? Did I mess that up here too?
Yeah.
Oh, sorry.
No, on the very top one should be negative one on the bottom.
Oh, yeah, right, the Sorry about that. Okay. Thank you. And remember, this value is approximately the square root of 1.1. So the input in the original function matches the input of the linear approximation. Is everyone clear with that? It can make a big difference in your computations. So we got this to come out to be 1.05. You know, this is almost something we can do in our heads, right? Because it's easy to take half a number. We just take the number to approximate the square root of a number that's close to 1. We just add 1 to it and then take half of that value. So we've got 2.10, half of 2.10 is 1.05. And that's a pretty easy thing. It's a lot easier than trying to think of the square root of 1.1. It's easier to add 1 and then half. The actual value was 1.048. That's a good approximation? That's pretty good. And part C, we're going to use the same process for approximating the square root of 0.1. So the square root of 0.1 is approximately L of 0.1, which is identical to saying 1/2 the input plus 1. So we have 1.1 divided by 2, 0.55. Where the actual value for that was 0.316. Is that a good approximation? No, I mean, it's not even correct to the 10th place. It's a pretty bad approximation. Are there any questions on what we've done, though, so far? Anybody have any questions on A, B, or C? So now let's think about this part C. And we'll ask the question, why was using the linear approximation to approximate the square root of 0.1 so bad? I don't know, bad's relative, so why was that approximation off a lot?
Is it because 0.1 was far from the origin?
Yeah, right, good. Not the origin, but
RA?
yeah, exactly, yeah, very good. So we constructed this particular linear approximation 1/2 x plus 1 with the point 1, 0, or 1 comma 1, right? So our A value, or the x value in which we fixed that line, was an x value of 1. So when we approximated the square root of 1.1, that's really, really close to where we constructed our tangent line. However, 0.1 is very far away from x equals to 1, where we constructed our tangent line. So that's why this approximation was bad. Because we constructed the linear approximation at x equal to 1 and since x equal to 0.1, again, far is a relative term, so I'll put that in quotations. Since 0.1 is far from x equal to 1, we obtained a bad approximation. Does that make sense? So let's look at that visually, just to kind of give us a sense on, you know, utilizing that linear approximation for 1.1 versus 0.1. We know it's identical, right, at the point, because we constructed our line to touch at that point. So the difference between the function f of x and the linear approximation at the point you constructed is nothing, because the tangent line touches at that point. So here's what we're looking at. We're saying, all right, to approximate the square root of 1.1, which is this point, instead of using the purple curve, I'm going to use this curve. So notice the scale on the right-hand side here. We go from 1.045 to 1.05, 6, 7, 8, 9. So each tick mark that we see in between is what, 0.01? So we have a difference between this point and this point of 0.01. Here's the line, here's the function. We're using the line to give us that value approximately. Then when we try to approximate the square root of 1.1, or 0.1 rather, now we're using the line again to approximate that, and we see that that's a much larger difference. It's a little bit more than half a unit away, as opposed to 0.001 unit away, right? So does that make sense? The difference between the line and the function for 1.1 was really, really small, because we constructed our line here. But as we move further and further away, we see sort of the separation of the line and the function. And that was approximately our linear approximation at 1.1. So those were virtually identical. This point down here, however, this is the actual value. And this is our linear approximation. It's almost like we can look at a graph and vertically measure the difference between the line and the function to tell us, or to see immediately that that's any of these x values probably from here to here to the origin are pretty bad approximations, and they just keep getting worse and worse as we get closer to 0. So how could we remedy that if we wanted a better approximation of the square root of 1.1? So question, if we wanted a better approximation of the square root of 0.1, what must we do?
Could we, in theory, pick a different A value and create a different equation?
Exactly, yep. So we would just choose a different A value to construct our tangent line. In other words, we need to construct a new tangent line with a value that's fixed closer to the point in which we're trying to approximate. So construct a different linear approximation using a value closer to A or X. It's really interchangeable. X is a variable. Once the variable is fixed, then they just call that A. And here A equals to, since we have to take the square root of it, the square root's involved, and the derivative, choosing A equals 9 over 100 and finding the tangent line there at that value is a good choice to approximate the square root of 0.1. We don't do any of that kind of stuff. We usually just construct the tangent line or the linear approximation and approximate values. So there's not a lot of moving that or reconstructing to approximate something different. But it is worthwhile to mention that we can do that. Do y'all have any questions?
Right here. When we're gauging this situation as far as whether or not it's a good A value for that, is there any kind of pattern or like percentage basis close to the value?
Just mean in general?
Yeah, just for like a good place to start.
No,
Okay.
not here. If you continue on to Calc 2, there's a lot of work developing what they call an interval of convergence.
Okay.
So with an interval of convergence, it sort of gives you, like, how accurate is this approximation around this point? So it would say that, maybe my interval of convergence is from here to here. And from that, we could say that the square root of x near x equals to 1 is valid as long as we're within this window. So we could use that approximation to approximate the square root of any of these inputs, but as soon as we get out of that interval, then it's no longer a good approximation.
Okay. Something to keep in mind for later.
Yeah. It's a good question, though. I mean, it's a very reasonable thing. Any other questions? Let's see what we have. Okay. Then changing gears a little bit. The second topic in 4.6 is related to the linear approximation. The notion of differentials. We'll define this in a minute, but let's consider a change in our independent variable from a starting value of A to a value of A plus delta x, where delta x denotes a change delta in x. We're going to look at two things here. One of them will be the differential, and the other one will not. So the first thing we're going to look at is the actual change in function values. Which we're going to call delta y. So we're going to use, your textbook uses delta y to denote the exact or the actual change in the function. Keeping in mind that x changes from a to a plus delta x, then the actual change in the function is pretty simply measured as f of a plus delta x minus f of a. So if I said the square root function, x changes from 1 to 2, how much did y change? You would just take the square root of 2 minus the square root of 1, right? You measure that exact change. Hopefully that's straightforward. Do you all have any questions on that? Okay, and the second thing that we want to look at is not the change in the function, but the change in the linear approximation. L of x, I'll just write it out here just to remind you, f of a plus f prime of a times x minus a. Remember, there's only one place we input the x, and that's at the tail end of x minus a. So the change in the linear approximation as x changes from a to a plus delta x. What do your textbook call that? Your textbook's going to call that delta L, the change in the linear approximation. And that's defined as L evaluated at a plus delta x minus L of a. Everybody get the roll sheet? So this notation for f of x is arbitrary because that wasn't given, but sort of in that arbitrary vein, we do have what L of x is equal to. So now let's take a plus delta x and plug it in to our L of x formula. Keeping in mind that a plus delta x is the input over here, and then I'll just highlight this. Okay, so now we're going to input a plus delta x in for x right there and get its f of a plus delta x plus f prime of a plus delta, or sorry, I told you not to do this and I just did it. The only input we have is over there at the very end. So this is still just f of a plus f prime of a times x minus a, where input is a plus delta x. All of that is L evaluated at a plus delta x minus L of a. Again, a goes in for x above here. So we have f of a minus f prime of a times our input minus a, which is a. Hopefully that shows up on the notes. Okay, so we can actually come up with a formula for the change in the linear approximation. But notice some of these things go away because we have the derivative on the far right, the derivative times a minus a, all of that's 0. We're left with the minus a here, sorry, minus f of a. So that simplifies to just minus f of a. With this f of a here, those two things will cancel, and we'll just be left with f prime of a, in parentheses here, the a plus delta x minus a. We're just left with delta x. So we get that the change in the linear approximation is f prime of a times delta x. That's the change. The change in the linear approximation. So remember, the linear approximation approximates the function. So if we say that that's the change in the linear approximation, then what that's going to give us is an approximate change in the function. Is everyone cool with that? So to distinguish between the actual change of the function and the change in the linear approximation is, let's go ahead and explicitly state that, is the approximate change in y. That is, the change in y is approximately the change in the linear approximation. So to distinguish between the actual change, the exact change of the function, and the approximate change of the function, we're going to change this notation of delta L. So we're going to take all of this stuff and just call this delta L. We're going to change that into lowercase dy equals to f prime times dx, changing the deltas into lowercase d's. And since this a was arbitrary, we'll just go ahead and use f prime of x. And then this will give us the approximate change. This was the delta L, which was the approximate change in the function. So we're just going to use this right here as the approximate change in the function. Approximate change. To the function y equals f of x. And then that's what we're going to define as our differential. I don't know. Okay, so there's a diagram below, just to make sure everybody has all of this. Just to kind of give you a visual sense of what we're looking at. Our function here is in black, and here we're changing the function from a to a plus delta x. So from this point to this point, what was the actual change in the function? The actual change in the function is just measured from this function value to this function value. Oops, that was pretty bad. So the difference from here to here, that's delta y. When we do the same thing but on the linear approximation, the red line, that's going to give us our dy. So the difference between going from this point, notice our tangent line is right there, it's tangent 2 at that point, to this point, that change, also from here to here, is measured by dy. So you see it's not exactly the same as the actual change in the function, but again, over like really small intervals, we would expect those to be identical, right? So this is a pretty large interval we're looking over. Imagine if we scoot this point to this point. So we're going to use what's the actual change in the function value from here to here versus the change in the linear approximation from here to here. Now that difference is a lot less than this difference. So that figure is not important that you capture. It's what's important is to know the formula and to understand what that formula tells you. So I guess I didn't. Oh yeah, I put it here. So the formula for the differential is this right here. I'll go ahead and highlight that. And what it says is dy, remember, it just measures a small change in your output. So it says, and if we want to measure a change in our output, then I have to know the dx, which is the change in the input, and I have to multiply that by the rate of change. So the rate of change multiplied by the change itself gives us the approximate change in the function. So let's see if they say the differential dx and dy. A small change in x is denoted by dx. And this is given as well as the function. Both the function and the change in x is given. Otherwise, it's just find the differential, and you've just got the formula dy equals the derivative times dx. So the only thing that changes in this formula is f prime, depending on what function you actually start with. The dy and the dx, they're always there as dy dx. And so what it says is, if I've got a function, and I want to know if I change my inputs by a small amount, how much does that affect the output? So like maybe I have a function that describes the volume of a sphere, right? And I want to think about like maybe if I change the input from 0 to 0.1, how much does that actually affect the volume of the sphere? Or whatever. You think of functions describing a multitude of things, but the differential says that given a small change in the input, we can measure how much that affects or changes the output. Okay, questions on any of that? Given a small change in x, find the change in y for 3 cosine squared x. So remember the small change in x, we're just going to denote as dx, and find the change in y, we're just going to leave that as dy. So all we're using here is the fact that dy is f prime of x dx. So all we need to do is find the derivative of that function and insert that into our formula here for f prime. Okay, so what is the derivative of 3 cosine squared x? Okay, negative 6 sine x.
Cosine x.
Cosine x, right. Chain rule. Okay, so that's it. That's all they asked for. So the change in y is negative 6 sine x cosine x dx. now we'll actually look at a couple of different values, or at least one. So on the function 3 cosine squared, any small change in the input will result in this change of the output. Do y'all have any questions on what we've done so far, or what that means? So let's look at some examples. Let's say x increases from x equals to pi over 4 to x equals to pi over 4 plus 0.1. Find the resulting change in y. Which was 3 cosine squared x. So dy is the unknown. That's what we're determining. In order to determine that, we have negative 6 sine x cosine x dx. So to compute that, we need an x value, and we need the value for dx. So what is the dx that we're going to plug in? Yep, dx is 0.1. Remember, dx just denotes the change in x. X changed from pi over 4 to pi over 4 plus 0.1. So the change was just by 0.1. And what's x equal to? Pi over 4. How do you know it's pi over 4? Excuse me. How do you know it's pi over 4, not pi over 4 plus 0.1?
The point is the change that it went.
Okay, so the 0.1 was just a step size away from the actual x value. Does everybody see that? If we go back to the actual where we kind of derived this, the change in x is measured from a to a plus delta x. So the change in x here is just that delta x, whereas x starts at a and gets moved over by that particular change. Okay. So dx is 0.1 and x is pi over 4. That means dy is equal to negative 6 sine of pi over 4 times the cosine of pi over 4 times 0.1. And I calculated that to be negative 0.3. So the change being negative, first of all, dy being negative, what does that mean? The change in y is negative, therefore the change in y is, or decreased, right? Because that's negative, it means it's decreasing. So let's put this, what we have, this dy equals to all of this in words. As x changes from pi over 4 to pi over 4 plus 0.1, the function y, which was 3 cosine squared, decreases by 0.3 units. If dy were positive, then that would be an increase. So I don't know, whatever that represents, it represents a profit function. You want to know if I change the price of my items from $1 to $1.01, how much does that affect my profit? So you could use this formula to measure those kinds of things. Do y'all have any? Sorry.
This is just an approximation, right?
Yeah, it's for really small changes, it's very accurate. But if x changed from like pi over 4 to 30 pi over 4, it would be a pretty bad approximation. Yeah. So it's remember, this came from the linear approximation, and the linear approximation was really good as long as we stuck close to where we found the tangent line at. It's the same for this approximation. If the change in x is very large, then typically that's going to indicate a bad approximation to the change in y values. Yeah. Any other questions on this example or this differential stuff in general? I probably, more than likely, I'll let you know if I decide to, but more than likely will not test you on the differential aspect, just the linear approximation aspect from this section. But you do have a few of these in your homework. So, are there any other questions before we close out 4-6? So I know that we only have 3 minutes. I do at least want to introduce the next section, just so we can start thinking about some of the implications. At 4.7, we're dealing with L'Hopital's rule. And so this section is dealing with limits again. We're back to looking at limits. L'Hopital's rule deals with or applies to limits of the form that evaluate directly as 0 over 0 or infinity over infinity. And with infinity, we mean any combination of positive and negative. And these two forms are called indeterminate forms. And indeterminate just means you can't determine the value, at least initially, as 0 over 0 or infinity over infinity. Indeterminate form just means, that is, can have any value. Sometimes 0 over 0 in terms of a limit is 1. Sometimes it's negative 36. Sometimes infinity over infinity is 1. Sometimes it's negative 15. It really could be anything. These forms arise from computing the limit as x approaches a on a quotient f of x over g of x. So keep in mind, when we write 0 over 0 or infinity over infinity, we don't mean explicitly divide those two things. We mean that the numerator is approaching 0 and the denominator is approaching 0. Or the numerator is getting arbitrarily large, and the denominator is getting arbitrarily large. So it's just a notation and context of limits, not to be taken literally. So we'll continue with this on Thursday.